and today what we are going to do is, so this part, right. So, today we are going to look at estimation error first. Yeah. So, what is the estimation error? So, estimation error. So, which is the second part in the error breakdown that we did earlier. So, the estimation error is the following. This is RD of HS minus RT of H. So, let us see what this is, right. So, this is RD of HS, right. So, both S and D are involved. So, let us be careful about what this is. This is the test error, of course, of the classifier chosen by our algorithm. We have not specified an algorithm yet, we will do that in a minute, but whatever the algorithm is, this is the test error of the classifier chosen by our algorithm. And what is this? This is in fact minimum H in our hypothesis class, RD of H, which is just the minimum test possible test error in H. That is what this is, right. So, this is the difference that we want to study, and let me just make some points here so that we are clear, right. So, we cannot hope to have a uniform convergence result here. Convergence result directly, right. So, what do I mean by that, right. So, what do I mean by that? I am saying that what is this studying? This is studying the difference between the test error of the classifier that my algorithm chooses from training data and the best possible classifier's error in H. Now, so what does uniform convergence do? So, if you remember, what did uniform convergence do? Well, we wanted to care about the difference between the train and the test error of the classifier chosen by the algorithm. But what did uniform convergence do? Well, I will not do it for the specific classifier that my algorithm chooses, but I will bound this quantity for any H that my algorithm might choose, and because for every H I am able to bound it, and so I will be able to bound it for the H that my algorithm chooses as well. That is the uniform convergence argument we made earlier. But what I am saying is that we cannot get such an argument, do such an argument for this, right. So, and that is simply because this is studying the difference between a fixed quantity, which is RD of capital H, right. So, that is like the best possible classifier's error, and maybe that is just 0.05, which means that the best possible classifier is going to make only 5% error, right. So, with respect to the underlying distribution. Now, I want to argue how good is the test error of the classifier that my algorithm chooses. I mean, how far is it away from the best possible classifier's test error? Again, if I have to plot this as 0 to 1, now let us say, I mean, just for pedagogical reasons, let us say we have 5 classifiers in my bag, right. So, H1, H2, H3, H4, H5, maybe their corresponding test errors are like this, right. So, this is RD of H1, this is RD of H2 and so on, this is RD of H5. Let me write it down so that we are clear what we are talking about. This is RD of H4. Now, so what do you think is, so let us say there are only 5 classifiers in my bag itself for the moment, right. So, now what is RD of capital H, right. So, in other words, what is RD of script H? Let us give this numbers. Let us say this is 0.2, this is 0.25, this is 0.3, 0.32, maybe 0.45, right. So, I mean this cannot be 1 in that case, that is okay I guess, yeah, it is just anyway not drawn to scale. So, maybe I want to extend this further, let us call this 1. Yeah. So, what is RD of absolute value of H? Well, RD of absolute value of RD of script H is going to be the smallest possible error of any classifier that I pick in my bag, which is going to be just this, right. So, this is the best possible classifier in script H. Now, what I am saying is that, so my algorithm looks at the data and picks some classifier which is HS, and that has some test error. Now, it could be potentially this guy itself H1, in which case the difference is going to be 0, but let us say the epsilon that I care about is 0.07, right. So, then I probably have this interval which is 0.13 to 0.27, and I might have potentially picked H2, right. So, and H2 strain test error is 0.25, but then I am still within my epsilon range for of 0.07 for the best possible guy, right. So, so now when I say I cannot get a uniform convergence, well, maybe for H2 I will get, but I cannot argue that every guy, every classifier's test error is going to be uniformly close to the test error of the best possible guy. That is simply not going to be possible, right. So, because some of them are going to be away. If I fix an epsilon, there are going to be some classifier whose test error falls within the epsilon interval of the error of the best possible classifiers, but then there are going to be some who are outside this interval, right. So, now in this particular example H3, H4 and H5 are all outside this interval, and so cannot get this guarantee, right. So, which means that I cannot hope to get a uniform convergence kind of a result naturally, because simply because there is only one good guy, right. So, that is the reason, right. So, there is only one value for RD of script H, and we want to see how close we are to that script H, and then we want to ask the question, as I get more and more samples, am I getting closer and closer to RD of script H? That is the kind of question that we are asking, right. So, which means that, so what does this indirectly mean? It means that we need to specify the algorithm sorry about that, to obtain HS, right. So, without saying which algorithm I am going to use to get HS, there is no point in even studying the estimation error, right. So, that is what I want to do, that is the first point I wanted to make. So, now having said this, let's see what algorithm we should use. Okay. So, what can be an algorithm? So, algorithm for estimation error, right. So, algorithm, well, of course, if you taken like a machine learning course, you might have seen several algorithms for binary classification, maybe logistic regression, maybe making some generative assumptions, naive Bayes, support vector machines, perceptron, whatnot, neural networks, whatnot, right. So, but here what we are going to do is we are going to look at a hypothetical algorithm. I will talk about all these practical algorithms a little later. I will connect it to what the hypothetical algorithm is a little later. But then for the purposes of our analysis, we want to see what is the simplest thing that we can do. The simplest thing would be the following, right. So, I have a training data and I want an algorithm which outputs some classifier whose train error is reflective of, whose test error is reflective of the best possible test error in the entire hypothesis class in which I am searching. So, what is the best thing I can do, right? So, I have only the training data. So, I have to rely on my training data to do something meaningful. So, what can I do? If you think about it, the most simplest and the most intuitive algorithm would be to choose HS as that classifier in my script H which minimizes my training error, because the only quantity that I have handle over is the training error. I do not know how to compute test errors because I do not know the distribution. So, the only thing I can do is minimize the training error, right. So, and such an algorithm is what is called as ERM, which stands for Empirical Risk Minimizer. That is what an ERM stands for, which is like saying I have a training data, I want to find that H in my hypothesis class which makes the least number of mistakes on my training data. And now I ask, can I comment about the test error of this classifier and its difference to the best possible test error that I could achieve by any classifier in H, right. So that is the question that we are asking, right. So now let us go ahead and study this quantity of estimation error for this particular classifier, which is the ERM classifier. Let us do that. Okay. So, we want to study the following quantity RD of HS minus RD of H, where HS of course is the ERM, that is important. In fact, let me write this as HS ERM, so that we are, we know that we are talking about ERM here, right. So, yeah. So, I am going to write this as follows. So, this can be written as RD of H, which comes from our data set, which is by empirically minimizing the risk, minus the training error of HS ERM plus RS of HS ERM minus RD of H. Basically, all I have done is I have added and subtracted and added this term. So, this is exactly the same. So, basically, I am adding and subtracting the training error of the ERM and then trying to analyze if something interesting comes out of it. So this, let us say this RD of H say is achieved by some H star. Okay. There is some classifier H star in my capital script H which achieves which has the least test error. Let us call that H star, right. So, then what are we essentially saying is, we want to study this guy, which is now we have split it into RS test error of my ERM minus train error of my ERM plus train error of my ERM minus test error of the best possible classifier, which I am going to call as H star. Okay. Now, what I am going to do is I am going to look at this term. So, the first term looks like the train and the test error, difference between train and test error of a fixed classifier, which is the ERM classifier. So, that is something that we can handle, right. So, we will come to that in a little later. But on the other side, we have a mismatch. We have the training error of the ERM and we are comparing it with the test error of the best possible classifier. So, what I am going to do is I am going to break the second term further and then make things a little bit more easier. So, I am going to write the first term as such, nothing changes there. This is just the test error of ERM minus the train error of ERM, that stays, plus this is the train error of ERM. And now, let me add and subtract, let me use a different color to make sure what I am adding and subtracting. So, this is the test error of the best possible classifier. I do not know, sorry, the train error of the best possible classifier. I do not know what the best possible classifier is, but let us say that still has a training error. If I had used that classifier to compute the training error on the data that I am given, well, I will get some number. So, I am going to add and subtract that number, right. So, and then the term stays. Okay. So, now the interesting part that has happened is that, well, this is a difference between train and test rather test and train of the ERM. These two is the well, we will come to that. So, the last term is the difference between train and test of the best possible classifier. So, now let us look at the second term, which is the mismatch term, which is like, you know, it is not a difference between test and train, but it is the difference between the training error of two classifiers. One is the ERM, one is H star. Now, let's think about this for a second and ask, what do we know about this quantity? We are taking the training error. You have a data set and you are computing the training error of two classifiers, one which is the ERM, the other is the best possible classifier that makes the least test error. Well, H star might make the least test error, but the ERM makes the least train error. That is why it is an ERM, right. So, by choice ERM is the one that makes the least train error. H star might make the least test error, but it need not necessarily make least train error, right. So, it might be the best possible for the test data, but it may not be the best possible for the train data, not necessarily, because of the, you know, the sampling itself, right. So but because ERM is the best possible for train data, it will have the least possible train error. That is why it is an ERM. So, when I compare its train error to any other classifier's train error, well, the ERM's train error should be smaller than any other classifier's train error, and in particular, it has to be less than or equal to the train error of H star. Well, H star is best for something else, not for the train data, right. So, which means that I know that this quantity is less than or equal to 0 because, you know, RS of H star is necessarily greater than or equal to RS of H ERM, right. So, why is this true? This is true since RS of H star has to be greater than or equal to RS of HS ERM by choice of algorithm, right. So, our algorithm picked the one with the least training error, and that is where we are using the algorithm. So, which means that this is less than or equal to 0, right. So, in other words, I can ignore that this second, you know, set of terms, which is this part, and then say that this whole thing is less than or equal to RD of HS ERM minus RS of HS ERM plus RS of H star, the fourth and the fifth term here, minus RD of H star. Yeah. So, what is less than or equal to? Well, this is the estimation error, which is the test error of the classifier picked minus the test error, basically RD of H, which is RD of H star exactly. Yeah. So, this difference is at most the sum of these two differences. So, the absolute value of this, let us say, what can we say about the absolute value? Well, I am going to write two steps together, I hope that is okay, is at most, well, the absolute value, the above thing, and then absolute value of A plus B is at most absolute value of A plus absolute value of B, and so I can write this as the, you know, RD of HS ERM minus RS of HS ERM plus absolute value of RS of H star minus RD of H star. Okay. So, this happens. So, now, you know, because this is an absolute value, right. So, it does not matter, right. So, RD of HS minus RS of HS or RS of HS minus RD of HS, because there is an absolute value. So, I can just write this as even RS minus RD. I mean, it is anyway the positive value that we are taking into account, right. So, that is okay. Now, I know that, you know, this is the sum of the difference between train and test error of the ERM and the best possible classifier. What I am saying is that, well, this is just going to be at most, I can call this this is at most 2 times the maximum among all H in H RD of H, or rather RS of H minus RD of H, right. So, I mean, of course, one of these will be bigger, right. So, and I can upper bound this by twice that amount, and that can be further upper bounded by the maximum difference between train and test in the whole of my hypothesis class H. Now, we can say that, well, what am I saying? What have I said? So, I have said that the absolute difference between what I need, which is the test error of my ERM and the best possible test error, is at most twice the absolute difference between the test and the train error of any fixed classifier in my hypothesis class. Which means that, so think of this as event A and this as event B, right. So, if A is less than B, then the probability of A is less than or equal to probability of B, which means that then you can see the probability of, maybe I will write it in the next page. So, this implies probability of RD of HS ERM, well, what implication is that if this term is greater than or equal to epsilon, if this is greater than or equal to epsilon, then that means that this guy is also greater than or equal to epsilon, because this is already greater than or equal to this term, right. So, so the chance that this is greater than or equal to epsilon, the whatever we care about, is at most the probability that 2 times max over H in H RS of H minus RD of H greater than or equal to epsilon, which is just the probability that max over H in H, well, RS of H minus RD of H greater than or equal to epsilon by 2, right. The 2 has just gone to the other side, and now what we are saying is that this is, if in a finite hypothesis class, I can replace this with a union bound. I can simply replace this with a union bound and say that, well, this is exactly what we did for our uniform convergence, right. So, what we have kind of massaged to bring to the right hand side is something that we already have controlled, which is the difference between train and the test error, the maximum difference between the train and the test error of any classifier that I choose, right. And now, I mean, basically what I am saying is that for the best possible classifier, right. So, if I ask, when I say best possible classifier, the ERM, for that algorithm it chooses the ERM. If I ask what is its difference between test error and the best possible test error, now that difference can be bounded by the difference between the train and the test error of any classifier in my hypothesis class. That is what we have argued, right. So, and it is critical that this is an ERM, right. So, if it is not an ERM, so this step does not follow, right. So, this less than or equal to 0 does not follow, and so I have to worry about the train and the test error. I mean, the difference between train error of the algorithm of the classifier my algorithm chooses and the test error and the train error of the H star, which minimizes the test error of the entire hypothesis class, and I have no clue about that quantity, right. So, because I do not have a handle over it. So, I have to somehow choose intelligently the algorithm, and this is what this is doing basically, and only in that case I will get I can bound the estimation error by the generalization error in some sense, right. So, but for a different tighter allowance epsilon. Okay, and this we know, right. So, by uniform convergence results we know that as n goes to infinity, we know this goes to 0. This is something that we already know, right. So, this is from uniform convergence. Now, I just want to make a point here, right. So, I am not negating the previous statement that I made earlier, that we cannot hope to have a uniform convergence result for this, right. There is no mismatch between these two statements. What I am saying is that this is to say that if we do not fix the algorithm, then we cannot have a uniform result that says that the test error of whatever classifier is close to the best possible test error. That is simply not possible. But once you fix the algorithm, which in this case is ERM, now what we have managed to do is we have managed to upper bound the estimation error by the generalization error, and that happens only if it is ERM, right? So, or at least if it's ERM, that happens, right? So that's I mean, this is not a necessity, it's a sufficiency thing, right? So if it's an ERM, this happens, and that's what has helped us to reach this, right? So there is no kind of mismatch here, and that is important to understand. Okay, great. So this means that we have bounded successfully the estimation error as well, right? So earlier we bounded the generalization error. Now what we are saying is we have also managed to bound the estimation error. So let's just put down a few points here for us to summarize with respect to where we are in the estimation world. So what have we said? We have said ERM is, you know, good. And I say good in the sense of, you know, the estimation error statistically. That is, if I blindly find that classifier which minimizes the train error, then as I get more and more data, two things are going to happen. One, the train error of the ERM is going to get closer and closer to the test error of the ERM, and the test error of the ERM is going to get closer and closer to the best possible test error in H. That is precisely what we are saying, right. So let me write that down. So when I say good statistically, as n goes to infinity, train error of ERM approaches the test error of ERM, right. So train error is what changes with n, and what I am saying is that the test error of ERM is fixed, right. So I mean, not fixed, because as n changes, the ERM changes, the test error also changes, but then these two guys get closer and closer to each other. Maybe that's the right way to say, right. So this difference goes to 0. That's the first thing. The second thing is that the test error, let me write it clearly, test error of ERM minus best possible test error in H, this difference also goes to 0, and this is a great thing, because both the generalization and the estimation error goes to 0, right. So which means that, you know, we have almost cracked what we want, right. So we initially said our, you know, if you go back to where we started, we said that our training error minus base error is divided into 3 parts: generalization, estimation, and approximation. Now what we are saying is that as I get more and more samples, my generalization error goes to 0, my estimation error goes to 0, right. So those two are what we have said so far in a statistical sense, right. So when I say good, it means that it has good statistical properties. That's what it means, right. So but typically ERM is computationally hard. While it has good statistical properties, right. So I mean, then I should be doing this, right. So why am I not doing this in practice? Because in practice this is usually very hard to find the classifier which makes the least training error, right. So that's a hard problem. So just to give a sense example, if H is linear, that is, we are just searching in the set of all W's such that, you know, once you get a W, sign of W transpose X is what you are going to use to make your prediction, right. So that's what H is linear means, right. So H linear, you know, means set of all HW such that HW of X is plus 1 if sign of W transpose X is it's positive, or let me just say W transpose X is greater than or equal to 0 and minus 1 otherwise, or 0, does not matter, that is just convention. So, this is my linear hypothesis class, right. So, if H is linear, then finding the minimum, H is parameterized by W. So, finding the minimum W, d-dimensional W, let us say such that my training error, which is sum over I equals 1 to n, indicator of W transpose X, sign of W transpose X not equal to Xi, not equal to Yi, right. So, finding that W, which makes the least train error, is NP hard, right. So, NP hard is non-deterministic polynomial hard, which means that well, the technical, let us not worry about the technical definition of NP hardness. It just goes to say that we do not have an efficient procedure to solve this. It just means that we might have to it might take exponential time to figure out what this W is. Exponential in the parameter size, right. So, in this case parameter size, let us say is d and n, it will take exponential time, and there is no efficient polynomial time algorithm that is known or expected to be developed for this problem, right. So, which means that though we prove that ERM is good statistically, we cannot compute that in practice, which is slightly disappointing, because we have a good statistically sound method, but not necessarily it can be computed, right. So, what does one do? One uses surrogate risks, right. So, risks or losses in practice, right. So, example, you might have logistic loss, and that will lead to logistic regression algorithm. You might have hinge loss, that will lead to the support vector machine algorithm. You might have exponential loss, that might lead to a variant of boosting algorithm, and so on and so forth. So, basically of course, I do not want to describe what these losses here in this course. So, I am assuming many of you might have seen this. If not, it suffices to say that we cannot directly minimize the train error, even if you are searching in a finite VC dimension hypothesis space like the linear hypothesis class. So, we have to rely on some other easily minimizable function, which is what is called as a surrogate loss. Now, the problem is I am not solving the original problem, right. So, all my statistical results so far have been for the loss is the number of errors and the fraction of mistakes that I make, the probability of making a mistake with respect to the true distribution, and so on. But now, if I am not doing ERM, I am doing something else. So, now one needs to study when does minimizing this surrogate loss or risk also helps me make a statement about the ERM's capabilities, or the what is called as a 0-1 loss, which is the fraction of mistakes that I am making, right. So, we are not going to look at that in this course, but people do study that. In a proper statistical learning theory course, we would understand that we can take a class of loss functions and then ask when can I make statements about the the estimation error of the classifier returned by minimizing this loss function. Let us say hinge loss. I do hinge loss, let us say I do SVM outputs something, and then I ask I can measure the fraction of mistakes that SVM's output makes on the training data, and I want to ask how good is this with respect to the best possible classifier that has the least error in my hypothesis class, right. So, the same RD of H minus RD of H star kind of a question can be asked, and you can, in some cases, if you choose your loss carefully, you can make such statements. By minimizing the loss, instead of ERM, if I do the loss minimization, that loss minimization will give me an output which has some good properties statistically also. And the general field that studies this is what is called as so calibration of losses you know, which we are not going to look at in this course, but in a proper statistical learning theory course. So I think this will also be spoken about. Okay, not in this course. But I just wanted to mention that, you know, in practice, I mean, all this is not completely useless, but this is the right way to progress, right? So we know what the bottleneck is now, because, you know, we have great algorithms with great statistical properties, but just that, you know, it's not possible to implement it. So we do something else, which is the best possible that we can do, closest to whatever this algorithm is. But then how can we relate these two? That is where the calibration studies help us.